Hi folks, and welcome back to another video related to turbulence models in OpenFOAM using the flat plate as a reference case. And in this video, let's talk about near wall treatment. Okay, it is general theory, so let's talk about what is happening here. Let's revisit the case and change some boundary conditions to see the behavior. So basically, we're very well aware of the behavior. So we have in the streamwise direction, we have transition, laminar, transition region, then become fully turbulent, but then also normal to the wall, we have a similar behavior. So we have a viscous layer that we say that roughly speaking, y plus less than 5. The flow is laminar, then the buffer layer, okay, that transitional layer, very energetic. So y plus between 5 and 30, and then you have the lock layer, the outer layer, that y plus more than 30. Remember, upper limit depends on the Reynolds number. So we subdivide our boundary layer like this, and depending where you put your first cell center, you can take a wall resolving approach or a wall modeling approach. And remember, try to avoid putting the first cell center in the buffer layer because it is a transitional region. We don't know very well what is happening there. Okay, so a little bit what happens when you have with the velocity profile when the flow is turbulent and laminar. So hopefully you get the idea. Then the two approaches that we have is wall resolving and wall modeling, and that is what we're going to address. Okay. So basically, a wall resolving mesh looks like this, a wall modeling looks like this, okay? So you can see clearly the difference that if you use a wall model, you save a lot of cells, but then also you need to have good implementation of the wall functions to capture the physics, which is something that the researchers have done, and we have very robust implementations in open source commercial software, namely also in OpenFOAM. They are very robust, okay, but they do have limitations. To remind you also that it's not only about the distance normal to the wall, it is also about resolving this span-wise and stream-wise distance, okay? When you start to resolve, also start to think about resolving these distances, no, stream-wise, span-wise, and this is particularly important for scale resolving simulation, DNS stuff, and transition to turbulence. As I mentioned, this is the most difficult simulation that you can do, in CFD, capture transition. There are very specific models for that, and we're going to visit those models just to show you a little bit the cost that you pay when you have wall resolving. So look at that, verify meshes close to the wall. So a wall modeling here, we're talking about average y plus something about 60 here, 1, and look at that, kind of you double your cell count, and even worse. Here we go now, another geometry, submarine, so 60 and 1, and look at that, kind of you follow that relationship that you double. And here since it becomes even worse, from 50 million to 100 million, and now think about as you go from 100 million to 200 or 300 million, since get very expensive. So that is the idea of the wall modeling, save computational resources, but could also get the same solution. So very important plot. I hope that you are familiar with this plot at this point. Okay, this is the best way to validate your results. If you don't have any reference value, experimental value, or even if you have those, always take your time and do this plot to see if your turbulence model is working as it should be. So this is u plus y plus value. We mentioned y plus less than 5. You use this correlation, y plus more than 30, you use this correlation, very well validated in fluid dynamics from the experimental and also simulation point of view. And then the buffer region, this one, neither of these correlation holds, so this is why we want to avoid it now. So this is a transition region. So we already look at this plot. Let me move here. What is happening now, how subdivide, also viscous layer, buffer, logarithm, and so on. So well, a comparison experimental and DNA simulation. So here, remember that we always want to look at the average, at the mean profile, but kind of look at that we have similar behaviors there. And what I was talking about, that the upper limit, okay, in this plot, u plus y plus depends on the Reynolds number. So here you can see that different Reynolds numbers, this region here is wider and wider and wider. Okay, so do not take it for granted that you see very often literature that they always say 300. No, it's this limit. It's not necessarily, depends on the Reynolds number. Okay, so more plots showing this behavior. Okay, so easily you can test that. In this case that we're doing the flat plate, just change the Reynolds number and you will see that this region will get wider or narrower. Then also there is some dependency in this profile depending on the pressure gradient and roughness and so on. So here you see that adding some pressure gradient, how it separates and so on. So favorable pressure gradient will have the tendency to match more this laminar profile. Okay, so some plots there, and here's where I would like to get the near wall treatment to remind you. So the shear velocity is computed like this. We need the wall shear stress, just to stress that this is not an actual velocity. It's just because we call it shear velocity because it has the same units. Then U plus is computed like this. Velocity parallel to the wall or parallel to the string lines, and the Y plus is computed like this. So when we're talking in OpenFOAM, we mentioned that you have the nut U and nut K. When you use the nut U, you are computing the Y plus and U plus, you are using these correlations, okay, to compute it. And one of the deficiencies of this is that, look at that, when you have separation or reattachment, recirculation, shear stresses can be 0, okay? So this is 0, and as you put this quantity here, you have a singularity, okay? So that can give you problems, okay? So a way around that one to avoid this problem, that doesn't mean that it's going to crash, it's going to run, but be aware of that you have that deficiency. There is another approach, the one called the Y star. Okay, so a little bit how things are computed. So if your flow is laminar, you can compute it like this. If your flow is turbulence and you want to integrate down to the viscous layer, you compute it simply like this, quite easy. But if you use the same relation to do it with wall functions, you are missing a lot of gradient information. So this is not correct. What we do there is that we find a link between velocity, okay, and shear stresses. The velocity free string and the shear velocity or shear stress, wall shear stresses. So we link here by using this correlation, okay? So that's what we're doing with the wall function. So usually we propose like this. Now look at that. Now I'm changing to U star. So we say that U star equal to Y plus this is less than 5. If it is more than 30, equal to this. Okay, so the idea we mentioned that you have this singularity, that this can be considered and that can give you problems. So this is the other formulation. So here you have the reference by Launder and Spalding, okay, and there is some mathematical how things are derived here, but this is what we get. Okay, talking about Y star formulation. So the shear velocity is computed like this, and the Y star is computed like this, and your correlation to link these different regions to the wall shear stresses stay the same, but now these quantities are formulated in a different way. So this is what we're doing. So see here that we don't have that singularity like with the previous definition, that shear stresses are 0. You can have no problems here. If they are 0, they don't appear anywhere. The only requirements that this quantity must be computed. This is the turbulent kinetic energy. That we have seen that the Spalart-Allmaras, the one that we have in OpenFOAM, is not computed. And be careful that this K is different to this one, okay? This is another constant. So a little bit what is happening and production term, how things are computed. So more details, you can find it in this reference. We're going to revisit that. Then when you are using wall functions, okay, then you set 0 gradient equal to 0 at the walls, and you can choose the different treatments, U plus, this is for turbulent kinetic energy, and U plus or Y plus, for nut in OpenFOAM. Something to mention as well, we have these plots, and let's say that the only thing that changes is U plus or U star is the definition of the quantity, but what is happening here is the same. So this is what is called the automatic wall treatment. So you have the wall functions, okay, this treatment that you use this one, it only works when you Y plus is more than 30. But you can say also, let me generalize things a little bit more. And let's say that because I know that these two correlations intersect somewhere, and somewhere about 11, 35, 12, depends on the constant. But let's say 12 or 11.5, I don't recall what I put in these slides. They intersect here. So what you can say that for values more than this intersection, use this correlation. For values less than this correlation, then that intersection point use this correlation. So this is what is called the automatic wall treatment, scalable wall functions that we have in OpenFOAM, okay? So, okay, you have the precise intersection here, and okay, less than this, use this one, more than this, use this, okay? However, this region, the transition region, small changes can look at that difference when you are transitioning from one regime to the other. So not necessarily this is the best approach. You can do it. It's good. It's better than just using the log law. Okay. This one will generalize. So when we talk about insensitive models, kind of they're doing this switching and so on. But there are some other approaches now. So look at that. We can use a blending function, decader one, and look at that switch from here to here in this way, or you can use the Spalding law to do that switch in the red line. And okay, so what is happening? Let me go here and to mention that there is not a single way to treat wall functions. No, there are many ways. So here I just mentioned a few of those treatments, but there are many ways to treat that, to do that treatment. Talking about the decader function, how to do that blending here, you have the reference, and this is pretty much what is happening. So this is implemented in Fluent. In OpenFOAM, it's not implemented. It is automatic or the Spalding wall function. So this is what happens, and this is how you blend from one region to the other. So it's a much better blending than just finding this intersection and using one or the other relation. Then we have the Spalding law. This is the Spalding law, and the Spalding law here is represented in red line, and see that it's doing this, blends to turbulence, and you have this. So using this correlation, you can now link, okay, your profile to the shear stresses at the wall. And then there are some other approaches, okay, so Hoffman blending, just to mention more approaches and so on. Okay, so this is, generally speaking, not what is happening with these wall functions, okay? There is a lot here. I don't want to go too much into details. Again, just to remind you that, okay, it's not about normal distance, also this distance here. Talking about when you take the wall functions, basically you are modeling everything here by linking the velocity and the wall shear stresses with this analytical function, the log law, okay? And well, some final remarks. So just to end here, just to show you some comparison, the same case so we elaborate so each of these circles represents to a cell center, so clearly you see the difference between a wall resolving wall modeling mesh, comparison of the profiles, velocity profiles, and so on. Okay, so you see that if you follow good standard practice, you choose the right boundary conditions, you know your numerics, you're going to get the same results. Okay, you have this case we're looking at Fluent, but the same result we get with OpenFOAM, so high re, low re. Then the production, okay, again in this case Fluent, but we have seen exactly the same results with OpenFOAM, and in CFD cookie also we compare this, CFD cookie 1 we compare this, and so on. Comparing meshes, now looking at the quantities, and we're looking here velocity magnitudes. So see that wall resolving, you solve everything, then wall modeling, kind of you put another black box within the black box of the turbulence model. Wall resolving when it comes to K, so by definition it's 0, and see that you have it here 0. Here at the wall it is a 0 gradient, okay? We'll take the value in the free stream. Then epsilon, so in this case will be K epsilon model. So this is a particular behavior, and later when we talk about the K epsilon model, we're going to talk about these functions and so on. Okay, but look at the different wall modeling, wall resolving, and so on. And we can check also different quantities, and when I was talking here turbulent dispersion rate and kinetic energy contours, and this is the one that I want to come back, that this is the turbulent viscosity, and kind of it's a very well-known behavior as I mentioned, that eddy viscosity ratio for general flows or the turbulent viscosity, they can be used to identify the boundary layer thickness, as their values usually peaks in the middle of the boundary layer. Okay, so usually you have boundary layer and analyze your flow, and you see that in the middle, they tend to peak, and that is another way to know that whatever you're doing is correct. It's this peak, you start to have it outside of the boundary layer, there might be a problem, or much closer to the wall also there might be a problem in what you are doing. So this is the general idea about near wall treatments. I hope I clarified things. I hope I didn't confuse you at a higher level. Let me bring now to the publications on the video description. You have this paper. So this is the paper by Spalding. It's a very nice paper. I recommend you to read it. So here he formulate this, the Spalding function. Okay, so it's an alternative to all this treatment. It's another way to do it. So very nice paper. And another one that I recommend, well, this is the one by Launder and Spalding, and they were the first one not to introduce this treatment of the wall functions and so on, and using the U star. So I have to say that the mathematics here is heavy. Okay, it's rough mathematics, but I think you're really careful and you're going to understand what is happening here. But in any case, just to mention the idea, that this paper is 74, I think, at that time. The computers were not so powerful, so this was a requirement to have this treatment because doing DNS, it was out of the question. So here you see that they do the mathematics, the explanation, they arrive to this equation, U star, U plus here. Okay, U star and Y star here. Interesting here also, you will see that there is a dependence in temperature. So later we're going to address that one, that you have also some similar treatment that some correlations intersect and so on in function of temperature. Okay, so we're going to talk about that in another video, but have in mind that exists. And probably the best reference that I think you can find about wall boundary conditions is this one. It's a fantastic reference. I recommend you to take a look. And just to bring back here, highlight a few things. Now remember, this is your friction velocity or shear velocity. Then here Y star and Y plus definition. So you can clearly see here, and you have different definition for K epsilon, K omega. You have it there. Very interesting paper. You go down, you have all this validation that we have talked about during all these videos and so on. But I want to go here down there. The Launder Spalding methodology, pretty much this methodology. So here now you have the equations, how things are done, and a nice explanation and so on, and how to derive these equations as well. So here you have high Reynolds, the wall functions. Then they talk also about low Ray and so on, different treatments and a lot of stuff here. So I recommend you to take a look at this paper. Fantastic, I love it. So with this, I think I don't need to address any more theory. Hopefully you have a better idea. Also, you can come here to the NASA website. They don't have anything about wall functions, wall modeling, but as you read different sections, you will see that from time to time they talk about that sometimes. So now let's go back to the actual case. So we're here and essay. So here what I want to revisit, okay, is the high rate and see different behaviors. So let's go here and let's modify just node. Okay, so let's discuss here. So this is not okay, but it will work. This is also not okay because we're not computing TKA, and these three are okay. So it's up to you to pick up one. Do not pick up this for wall modeling because you're going to get the wrong result. This is a specialization of the wall function for verifying meshes. So that is not correct. Be careful about that. And this is not only for the Spalart-Allmaras of any model, so you need to know a little bit your theory. So what I would propose here, because I already have the figures, but I want to show you something, is let's do this. Let's use this one, that theoretically this is wrong, the rest nothing changed. And let me launch this case, run all, and there you go. So you see that it's running, and honestly, I think this should crash immediately, but developers make it run. But if you look at this, immediately you will realize there is something that is not good. Look at it, Y plus is 0. So this is already telling you that is something wrong. So be extremely careful about this. And if you run also with no low, you are going to get Y plus. It will make sense, but then when you plot the results, things are not correct. But look at that, it's perfect. It's running, things make sense. You compare with also results that with the other results, and you recall the other simulations, you will see that the values are kind of around the ballpark, you know, those values. But here, I already have all those plots. Let me go here. We're going to focus in F3 now, the friction coefficient. So we have the first one off. So off means that I took this and I use this value here. Fixed value, okay? So put it off and look at that. This is what we have. You have a solution, but it's not a correct one. So look at that. In this case, we're over predicting the friction coefficient. We're not matching this one. So when this one is below this line, it is over predicting. And basically it is over predicting now because I put this value. If you reduce this value, probably you put -8. Maybe you will get closer to match that one. Okay, so it depends on this value. So what we're doing here is fixing the value there at the wall, which is not correct because we know that value is non-uniform. And here, let me rant a little bit about AI machine learning, because a lot of people use AI machine learning to do this stuff. And hopefully you got an idea that you need to know a little bit the theory, there's some physics behind. It's not just getting a whole bunch of data and trying to fix that. So there is a reasoning behind what we're doing. So that's why I criticize a lot now using machine learning to calibrate coefficients or get better initial conditions, numerical values, and so on. In any case, I don't want to rant too much about that. It works. AI machine learning, it works, but as I say, it works when you don't have equations. In this case, we have governing equations. We have a lot of knowledge. So let's take advantage of that. Okay, so I digress a little bit. Let's move here. So this is what we have. So we have the solution there. Then we post-process. So see that get a solution is wrong. Now let's move to the one that we just run, nut k. So you see here that nut k will be y star. So corresponds to this result. So now y star again is something wrong. So now it is blending towards not the laminar, so it is under predicting. So you see that the shear here, your CF is very low. So again, results are wrong. Okay, need to know your theory. So there I presented these two variations. Okay, exactly the same observations applies to any turbulence models. Okay, so I'm using this one because I want to introduce all this Spalding and so on, but all the same observations apply. So as I mentioned, for high-rate Spalart-Allmaras, the best one is the nut U. The nut U, you use the U plus normal formulation. So maybe if you have separation, shear stress is 0 there, you have that singularity, but it's not a big deal. No, it's okay. So numerically speaking, there all that division by 0 is avoided. So now also we have the plot, and that one will correspond to y plus. And there you go. These are the correct results. Okay, not a problem there. Then you can go and use the low re. Okay, remember when you see something new that you don't know what is it, you can interrogate the source code. So let me go here, paste there, and there you go, the location. So, which by the way, here you have the location of all wall functions. And if you look at the header of this one, the header file of this one, you are going to get a brief description of what is happening there. So copy more, not always, hopefully. I think if I would recall, there is a brief description. And yeah, this boundary condition provides turbulent kinetic energy viscosity for low rate models. So this is specialized for low rate. So that automatic treatment does not apply. So if you have some regions that your y plus is larger than 30, or you are in the buffer layer, it's going to give you problems. And to remind you that what I'm talking about is that when you get the automatic treatment, okay, and that will be automatic one, this one, okay, it's not going to work. Okay, you have to be sure that your y plus, it is below, let's say 5 or 3. Okay, be careful about that. So the other one that we have here, it is the low, okay, the one that we're studying. So let me open that one, and actually I don't have the plot of that one. So let's run this one. Okay, so I know that the results shouldn't be correct in this case. So just to demonstrate, let's go here, let's put it there, let's run all there. And while we're getting the results, let's talk about, because the other one that we have is the Spalding, okay? So at this point, we're running with this one, but then we have the Spalding, and we already in the previous video talk about that seems to be okay, but then here you have this strange behavior. This doesn't mean that it is wrong implementation. It might be a case that you need to change a little bit on the relaxation, numerics, iterate a little bit more, who knows? Remember, all these cases I'm fixing numerics on the relaxation and number of iterations to 2000. So maybe you need to iterate a little bit, I don't know. But in any case, it makes sense, but you have this strange behavior. And if you compare with the nut U, okay, this is not correct. Let's see the right one. Spalding, the plus, this one. Okay, you see that everything makes sense except that region. Okay, so we're now hopefully getting a better gauge of what is happening with boundary conditions. And at this point, okay, we're almost done with the nut low. And just to point out that look at the nut low is running, but look at the values of y plus. It's kind of getting closer to this buffer layer. And as you recall, all the previous cases, it was something about 88, 90, 100, the average value. So this is already telling me that there is a problem with the prediction of the shear stresses. It is under predicting or over predicting. So at this point, let's open here, build in, delete load state and paraview state 3, go there, and there you go. So this is what we have in this case. And pretty much, you know, let me go save a screenshot so you have that F3 lower rate. Save, in my case I save like this, and just to make sure, look at that, you have it here. So see that the wrong behavior we have here. So again, we should correct now the wall shear stress here. So I didn't correct that one. So let's see here, but it's not like it's going to improve. So already see that this value is completely different from the previous values that usually is 12, now 0, 0, 12. Now you have it there. Now we go to this value, let me put it there, and there you go. So you get that and see that it's extremely completely wrong result. So because we're using the wrong boundary condition now for this model. So at this point, I think we're done. Now I hope you have a better idea what is happening and how to set your boundary conditions. So let me go back, and to be sure that I'm using the right ones, I put it there. And that's it. So bringing back my slides here, and will be this. Here, basically everything that we did, we can summarize it in this table. So here you have all the different combinations. So here I give some ways to compute the values, estimate now, but always now take a look at the references to see what is happening. So yes, always now look at the reference and be sure now to use the correct values. Okay, so we have all our combinations here and so on. So if we move to different models, then we're going to start to use the excellent one. Then we have some other, the omega we already used it. Then I didn't put here, well, we have the R1, the Reynolds stresses, but the Q zeta and the V2 I didn't put here, but those are very straightforward to set up. So that being said, let's move now to the low rate case. And in the low rate case, it's pretty much the same, okay? So let me open here. And exactly the same observation. So this is not correct, okay? Probably you can try to change the fixed value to match the correlation, but that's not correct at all, okay? Then this one is going to give you wrong result because you are not computing K. Just to stress that there are some Spalart-Allmaras models that can compute K using an algebraic equation. and actually I'm working implementing that. Then you have the y plus base, so just put it like this, and this y plus base, it is an automatic treatment. Okay, so this y plus base, it is going to do this stuff. Okay, then you have this one, it is just wall resolving, and then the Spalding, which is a continuous one. So as recall the plot, it will be this continuous plot, no? That is going to do the whole blending, so it will link the outer velocity with the shear stresses and so on. So yeah, I guess I don't need to run this case. No, we already know what to expect, but here we have now the results. So if we look at the y plus, Spalding, and nut low, they're all correct, no? So here, y plus, perfect match. Then Spalding, contrary to the previous case in the high red that you have that strength behavior here disappearing. So this is telling you that probably have a better behavior with wall resolving, not necessarily, as I say, might be something in the numerics, but there is that observation. And then the low red, that now look at that it perfectly works in this case. Okay, we didn't have the problem like in the previous high red, so we were using the wrong boundary condition in the wrong case. So there you have. I have to say something that I don't like to use this one because I don't see improvement, and sometimes I get strange results. And actually, because you need to be very sure that your y plus is less than 3 or 2, it needs to be low. So if you start to get in some regions y plus 10, 20, it's going to give you problems, no? So in this case, it's easy to get a very low y plus. Airfoils and more complicated geometry things are different. So just to end here also that, no, I didn't have there the residuals. So I wanted to plot the residuals, and actually let's do the exercise. So let's run the case, then using the magic of video editing, we get the final result immediately. But what I will propose to do, just to show you, low red, and let's change here, and well, will be up to you to choose. So let's rerun this one. So as I say, this is my choice. Okay, I really like this one. Okay, even if we observe that small strange behavior in the high red, but there is no problem. So I will use this one, but you can go for the new U as well. So it's up to you, or you can entirely switch it off and you will see that it's going to give you wrong results. So let's take a look at what is happening here. Run all, and perfect. Everything is smooth. Look at that. Your values here, everything makes sense. Okay, you are computing, I want to remind you, just one equation. So in comparison with 2 equation models, it should be less expensive. Okay, and what is running? Let me go on Python plot washer log solver, and there you go. So at this point, let's wait to have the final solution. Okay, so we reached the end of the simulation. So as you see, everything went smooth, no problems at all. You have your solution, the standard post-processing. So in this case, we use the Spalding one, so we should get these results. Then remember that we have this plot also, very nice. You can compare with the reference, the paper, and check now that you have now here, now the production, destruction, and so on is following the same behavior as in the reference. In this case, as we don't have the 2 equations, we cannot get, the other behavior that we know that production is in the buffer and so on. It's a syntactic model, and then the classic validation here. So yeah, there you go. Hopefully now at this point it's clear to you how to compute, how to set the boundary condition for wall functions and what is happening. Remember to enable wall functions here in boundary. All the walls needs to be defined as wall. When it comes to numerics also, depending on the method that you are using, some methods are going to ask you, to define this. Well, this in this case it requires, so it will be this one and the K omega SST family of models and a few other methods. So we show in the previous video how to get now that keyword to know what methods require that. But apart from this, nothing changed. Numerics, everything is exactly the same. So here, as I mentioned, we're fixing all these parameters in this case. So in the case of high re, which by the way, I think for high re, I use on the relaxations a little bit lower, because I know that if I increase that, it can give me some stability problems. So probably it can be related to this. Okay, so as they're a little bit lower, maybe you need to iterate more or try to increase it, or you can change numerics, something else. Okay, it's not say that the problem is the Spalding condition, boundary condition for the behavior that we were observing now here, which will be this one. Okay, so this is trend behavior. Is not say was the wall function, might be numerics. Okay, so who knows? So there you go. That is a nice exercise now to know what is happening there. So at this point, I'm done with the Spalart-Allmaras. Okay, and now in the next videos, we are going to move to another family of models, which is the K epsilon. Okay, there are many variants of the K epsilon. Okay, so we already covered here, and all these family of models, we're going to start to talk about this. These two also classify on the K epsilon family of models. So thank you for your attention and see you next time. Bye.